Have you ever paused to truly consider the stuff beneath your feet,
Mm,
the very fabric of our world,
mm.
from towering mountains to the microchips in your hand? It all begins with Earth's most fundamental building blocks.
Absolutely. It's easy to overlook.
So today we're taking a deep dive into matter and minerals, drawing our insights from Tarbuck, Lutjens, and Tassa's Earth, an introduction to physical geology.
A classic text.
Right. Our mission is to explore not just what minerals are, but why their unique structures and formation processes dictate so much about our planet and, well, our daily lives,
Hmm.
all without needing to crack open a textbook.
And it's a journey that quickly moves beyond just basic definitions, I think.
How so?
Well, understanding minerals is really the key to unlocking the mysteries of these huge geological processes and the volcanic eruptions or
Yeah.
the slow march of mountain building, maybe even the forces behind earthquakes.
Wow, okay. Big picture stuff.
Definitely. But it also connects directly to our lives, right? The copper in your phone wiring, the gold you might wear, gypsum in your walls, or, the quartz that defines so many landscapes.
Right, they're everywhere when you start looking.
Exactly.
Yeah.
These aren't just pretty rocks, they're the essential components of pretty much every resource we use. So this knowledge is absolutely foundational.
That's a powerful connection right from the start. Okay, so let's cut to the chase.
Mm-hmm.
What defines a mineral in geological terms?
Mm-hmm.
Because the word gets tossed around a lot, doesn't
Mm-hmm.
it? What makes something a mineral and not just, say, a cool-looking rock?
Right. Well, for geologists, a mineral has five non-negotiable characteristics that separate it from, well, everything else.
Five rules. Okay.
First, it must be naturally occurring.
So Earth-made.
Exactly. This immediately excludes anything lab-grown, like synthetic diamonds, no matter how identical they might look chemically or physically.
Got it. Rule one, natural. What's two?
Second, it's generally inorganic, so it doesn't come from organic compounds like, say, sugar. Though, interestingly, there's a bit of a gray area. Marine animal secretions, like calcium carbonate that forms shells.
Like seashells.
Yeah, precisely. When those get incorporated into the rock record, they do qualify as minerals, but generally think non-living origin.
Okay, so natural, mostly inorganic. What's next?
Third, it must be a solid substance at the temperatures normally found at Earth's surface anyway.
Makes sense.
So ice is a mineral, for example.
Right, H2O in solid form.
But liquid water isn't. The only notable exception found in nature, a natural liquid that's considered a mineraloid by some, is mercury.
Huh, interesting exception. Okay, solid, number four.
Fourth, and this is really crucial, it possesses an orderly crystalline structure,
Meaning?
meaning its atoms are arranged internally in a precise, repetitive, three-dimensional pattern, like a tiny, perfect lattice.
Oh, okay.
This internal order is why some minerals grow into those beautiful geometric crystals we sometimes see.
Like quartz points or salt cubes?
Exactly, and it's why volcanic glass, like obsidian, it's naturally occurring, it's solid,
But
but it lacks this internal atomic order. The atoms cooled too fast to get organized, so obsidian is not technically a mineral.
I'm tracking. So not just solid, but structured internally, deep down.
Hmm?
And the fifth characteristic.
Fifth, it must have a definite chemical composition, which we can express with a specific chemical formula. Think quartz, always SiO2.
Always that ratio.
Right. Now, there can be slight variations. Sometimes similar-sized elements might substitute for each other within that structure.
Like swapping out one type of atom for a similar one.
Exactly, without changing the fundamental internal structure. But the core recipe, the basic chemical identity, is fixed.
Okay, that nails it down. Natural, inorganic, solid, ordered structure, definite composition.
Those are the five keys. So when you see mineral oil on an ingredients list or hear about a lab-grown diamond,
But they don't meet the geological definition.
precisely, they might share some properties, but geologically speaking, they're playing by different rules. That natural internal order is what truly defines these fundamental building blocks of our planet.
That distinction is key. And that brings us nicely to the difference between minerals and rocks, doesn't it?
It does. Most people use the terms interchangeably sometimes.
Yeah, so most rocks, like granite, for instance, are actually composites, right? Aggregates of several different minerals all stuck together.
Exactly. You can often see the individual grains if you look closely, maybe some glassy quartz, some black hornblende, some pink or white feldspar, all in one piece of granite.
But not all rocks are like that.
No, some rocks, like limestone, are almost entirely made of just one mineral. In limestone's case, it's mostly calcite.
Okay.
And then you have materials like obsidian or pumice volcanic glass, again, which are definitely rocks.
But not minerals.
Right. Because they lack that crystalline structure we just talked about. They're non-crystalline solids.
It seems like such a basic distinction, but it clarifies a lot.
And this foundational understanding is actually ancient. Humans were interacting with minerals for millennia without knowing the chemistry, of course.
Like using flint for tools.
Exactly. Flint and chert for tools and weapons. And then came mining gold, silver, copper as early as, what, 3700 BCE?
Wow, that far back.
Yeah, and those early mining efforts ultimately led to discoveries like bronze, mixing copper and tin, which literally shaped early civilizations. Our early technologies were built on these materials.
It's amazing how these basic definitions have such deep historical roots. Now, to truly grasp why minerals behave the way they do, why some are hard, some soft, some split easily, we have to zoom in, right?
Yeah.
Way past what our eyes can see, down to the atomic level.
Absolutely. It all comes down to atoms and how they bond together.
And specifically, it's the valence electrons, those electrons in the outermost shell of an atom.
You've got it. They're the ones involved in chemical bonding. They're the movers and shakers, constantly striving for
The
stability.
stability meaning.
Well, atoms bond to achieve a more stable arrangement, typically by gaining, losing, or sharing electrons to complete their outermost shell. There's a concept called the octet rule. Atoms tend to want 8 electrons in that outer shell, like the stable, noble gases. Okay, they want that full outer shell.
Right. And it's this fundamental drive that leads to the main types of chemical bonds, which dictate pretty much everything about a mineral's properties.
Okay, let's break those down. The first type, ionic bonds, that's all about transfer, right? Give and take.
Exactly. One atom essentially donates one or more electrons, becoming a positively charged ion.
Occasion.
Right. While another atom accepts those electrons, becoming negatively charged an anion.
Okay.
These oppositely charged ions then strongly attract each other, like tiny magnets. The classic example is sodium and chlorine forming halite, our common table salt.
NaL.
Precisely. Sodium gives up an electron, chlorine takes it. And what's really astonishing is how the individual components change. You start with poisonous sodium metal and poisonous chlorine gas.
Definitely wouldn't want those on my fries.
Not at all.
Yeah.
But through this simple electron transfer, they transform into harmless, essential sodium chloride. The properties change dramatically. That's a powerful illustration of how these tiny interactions rewrite the rules at our scale.
Okay, so that's ionic transfer. Then there are covalent bonds. What's happening there?
Here, instead of transferring, atoms share electrons to achieve that stable outer shell.
Sharing, okay.
Think of two hydrogen atoms coming together to form an H2 molecule. Each shares its single electron with the other, so both effectively feel like they have 2 electrons, filling their innermost shell. These shared electrons create a strong, stable bond holding the atoms together.
So a different kind of connection, leading to different properties.
Completely different. And then finally, a very unique bond type found in metals, metallic bonds.
How do those work?
Well, these are truly fascinating. In metallic bonding, the valence electrons aren't tied to specific atoms, nor are they just shared between 2 atoms like in covalent bonds.
So where are they?
They're freely shared in a kind of sea or cloud that moves among all the atoms in the metallic structure.
A sea of electrons. Exactly. And this mobile sea is precisely why metals like native gold or copper are such excellent electrical and thermal conductors. The electrons are free to move and carry charge or heat.
Ah, okay. That makes sense.
It also explains their malleability, why you can hammer them into thin sheets, and their ductility, why you can draw them into wires.
Yeah.
The atoms can sort of slide past each other within that electron sea without breaking the overall metallic bond.
Unlike ionic or covalent solids.
Which tend to be brittle, right? They shatter when you hit them because you're breaking specific localized bonds.
So ionic, covalent, metallic. These bond types explain so much.
They really do. And it's worth noting that many common silicate minerals, the most common type in Earth's crust, actually feature bonds that have characteristics of both ionic and covalent bonding. It's often a spectrum rather than neat boxes.
A bit of a hybrid situation.
Exactly. But it's astonishing how these seemingly tiny atomic interactions, these different ways of holding atoms together, don't just create matter, but fundamentally dictate everything about a material. Its hardness, its cleavage, its conductivity, how we can shape it, where we even find it concentrated.
It truly is the microscopic blueprint for the macroscopic behavior we see.
Okay, so if these tiny bonds are the architects, where do they actually build these mineral structures? How do minerals come into being?
Great question. They form through several key processes.
And one incredibly common way is through precipitation from solution, right?
Yes, absolutely. Picture this. Water, maybe groundwater or seawater, becomes saturated with dissolved mineral matter ions floating around.
Like super salty water.
Exactly. Then, if that water cools down or if it starts to evaporate, the dissolved ions can no longer stay dissolved. There isn't enough water or energy to keep them apart.
So they start looking for partners. Pretty much. They start bonding together, arranging themselves into that orderly crystalline structure, and forming solid mineral crystals that precipitate or fall out of the solution.
Where do we see this happening?
You can see this writ large in places like the Great Salt Lake in Utah or Bolivia's Salar de Uyuni, that immense salt flat, which also happens to be a vast lithium reserve.
Ah, lithium for battery.
The very same. These are huge evaporate deposits formed as ancient bodies of water evaporated.
Wow.
We also see precipitation happening on a smaller scale, like inside cavities or fractures in rocks. Groundwater carrying dissolved silica, for example, might slowly deposit quartz crystals inside a void, creating those spectacular crystalline geodes.
Like amethyst geodes.
Exactly. That's precipitation at work.
So evaporation and cooling of water are key drivers. What's another major process for mineral formation?
Another huge one is the crystallization of molten rock.
Magma or lava?
Precisely. When hot magma, which is molten rock deep within the earth, or lava molten rock erupted at the surface begins to cool, those atoms and ions that were moving around freely start to slow down.
Losing energy.
Yes. And as they slow down, they begin to chemically combine and arrange themselves into crystalline structures. The first tiny crystals form and then grow larger, often interlocking with other mineral crystals forming nearby as the entire mass solidifies.
And this forms.
This is the very genesis of all igneous rocks, which make up a huge portion of Earth's crust and mantle. Think granite, basalt. They're born from cooling melt.
So we have precipitation from water and crystallization from melt. It seems very physical, chemical. But you mentioned biology plays a role too. That sounds surprising.
It does, and it's a really fascinating aspect. Minerals also form through biological processes. Life itself builds minerals.
How did that work?
Well, many water-dwelling organisms literally extract ions dissolved in the water around them.
Like calcium or silicon?
Exactly. They extract these ions and use them to create mineral matter for their skeletons, shells, or other hard parts.
Like corals building reefs.
Perfect example. Corals, and also mollusks like clams or snails, pull calcium and carbonate ions from seawater to build their structures out of calcium carbonate, the mineral calcite, or its polymorph aragonite. Over time, these can accumulate to form massive reefs or thick layers of sediment that eventually become the sedimentary rock limestone.
So limestone mountains might have started as shells?
In many cases, yes. Even microscopic organisms play a huge role. Tiny plankton like diatoms and radiolarians produce intricate skeletons made of silica, SiO2.
The same stuff as quartz.
Essentially, yes. Amorphous silica first, which can later crystallize. When these organisms die, their tiny silica skeletons rain down on the seafloor, accumulating into layers that can eventually form rocks like chert or flint.
Flint, like the arrowheads.
The very same. So this biological deposition is a huge, often underappreciated part of Earth's grand mineral cycle.
And these processes aren't just academic curiosities. They have immense economic implications, don't they? To make valuable minerals, like gold. How does that fit in?
That's an excellent point. Gold formation often involves hydrothermal solutions, hot water dissolving gold, and other elements deep underground. As these solutions move towards the surface and cool or react with other rocks, the gold precipitates out, often in quartz veins.
So precipitation again, but with hot water.
Often, yes. Our source material actually highlights the Superpit in Western Australia, one of the world's largest open-pit gold mines, as an example of where these geological processes have concentrated gold.
And gold's value is obvious: jewelry, currency.
Electronics, even specialized uses like in dentistry or gourmet food, its value comes from its rarity, beauty, and also its properties. It's very unreactive, which is why it doesn't easily tarnish.
And why it's often found as a native element, right? Pure gold.
Exactly. Its low reactivity means it doesn't readily combine with other elements, so it can be found in its pure metallic state. This ties directly back to its atomic nature and the formation processes that concentrate it. The story of gold is a perfect illustration of a mineral's inherent properties meeting geological opportunity.
So we have all these minerals forming in diverse ways, through different processes. But let's say we're out in the field or in a lab faced with an unknown sample. How do we actually identify it? It sounds like being a geological detective.
That's a great analogy. You use a whole suite of physical properties as your clues to figure out the mineral's identity.
Okay, where do we start? What are the first things to look at?
Often you start with how it interacts with light, its optical properties. One of the most immediate is luster.
Luster, like shininess.
Basically, yes. It's how light reflects off the mineral's surface. The main distinction is usually between metallic luster, looks like polished metal, and non-metallic luster.
And non-metallic can vary a lot.
Oh yes, non-metallic lusters include vitreous, glassy, like quartz, dull or earthy, like dry soil, pearly, like a pearl, often seen on cleavage surfaces,
Yeah.
silky, like satin cloth from parallel fibers, or even greasy, looks like it's coated in oil. Luster is often the very first clue you notice.
Okay, so how it shines. What else optically?
Next, you check its ability to transmit light. Is it opaque, meaning no light passes through? Is it translucent, where light gets through but you can't see clear images through it? Or is it transparent, like window glass, where you can see right through?
Opaque, translucent, transparent. Got it. What about just color? Isn't that obvious?
Well, color is often the most tempting property to use, but it can actually be quite deceiving.
Why that?
Because even tiny amounts of impurities can drastically change a mineral's color. Quartz, for example, pure SiO2 should be colorless, but add a trace of iron and you get purple amethyst, a bit of aluminum and radiation, maybe smoky quartz. Titanium might give you rose quartz. So quartz can be clear, white, pink, purple, yellow, brown, gray, even black.
Wow. Okay, so color's unreliable. What's better?
A much more reliable property is streak.
Streak.
Yes, it's the color of a mineral's powder. You find it by rubbing the mineral across a piece of unglazed porcelain, a streak plate.
Why is the powder color better?
Because the streak color is generally much less variable than the color of the whole crystal. It sort of cancels out the effects of impurities or surface tarnishing. Think of it as the mineral's true underlying color, its signature.
That's clever. Does it help distinguish types?
Definitely. Metallic minerals typically leave a dense, dark streak, while most non-metallic minerals leave a light-colored or white streak. It's a great diagnostic test.
Okay, so luster, light transmission, be careful with color, use streak instead. What about the mineral shape?
Ah, yes. The mineral's characteristic crystal shape, or crystal habit, is another important clue. This describes the typical shape its crystals tend to grow in when they have room to form freely.
Like cubes or pyramids?
Exactly. Some minerals commonly form equant crystals, roughly equal dimensions like garnet. Others are bladed, long and flat, or fibrous like threads, or prismatic, elongated like a pencil. Halite and fluorite often grow in perfect cubes. Pyrite can form cubes or octahedrons, or even crystals with 12 faces called pyridohedrons.
So even one mineral can have different habits sometimes.
Yes, the habit can be influenced by the specific conditions during growth, but many minerals have a common or preferred habit that aids identification.
Okay, so optical properties and crystal shape give us visual clues. But beyond how it looks, a mineral's strength, how it responds to stress, tells us a lot about its internal atomic bonds, doesn't it?
Absolutely. This is where we get into properties like hardness, cleavage, fracture, and tenacity.
Let's start with hardness. That sounds straightforward.
It's a mineral's resistance to scratching or abrasion. We measure it using the Mohs scale, which is a relative scale ranking 10 minerals from 1 softest to 10 hardest.
10 being diamond.
10 is diamond, the hardest natural substance. 1 is talc, which feels soapy, and you can scratch easily with your fingernail.
So you can use common objects to estimate hardness.
Exactly. Your fingernail has a hardness of about 2.5. A copper penny is around 3.5. A piece of glass is about 5.5. A steel knife blade is usually around 5.5 to 6.5.
So if mineral scratches glass, it's harder than 5.5.
Right, and if glass scratches the mineral is softer than 5.5. Quartz, which is very common, has a hardness of 7, so it easily scratches glass. It's a very useful field test.
Okay, hardness. What about cleavage? That sounds like how it breaks.
It is, but in a very specific way. Cleavage is the tendency of a mineral to break along planes of weak bonding within its crystal structure.
Ah, breaking along the weak links.
Precisely. Because the bonds are weaker in certain directions, the mineral splits easily along these directions, producing smooth, flat surfaces called cleavage planes.
Can you give some examples?
Sure. Mica minerals, like muscovite or biotite, have perfect cleavage in one direction, allowing them to split into incredibly thin, flexible sheets.
Yeah, you can peel them apart.
Right. Feldspar, another very common mineral, typically has 2 directions of cleavage that meet at nearly a 90-degree angle. Halite, salt, has three directions of cleavage, all at 90 degrees, so it breaks into cubes. Calcite also has three directions, but they're not at 90 degrees, so it breaks into rhombohedrons, slanted shapes.
So the number of cleavage directions and the angles between them are important clues.
Crucial clues, and it's really important not to confuse cleavage with crystal habit. Habit is the shape it grows in. Cleavage is how it breaks due to its internal structure.
Got it. So what if a mineral doesn't have weak planes? How does it break then?
If the bonds are roughly equal in strength in all directions, or if it lacks that crystalline structure altogether like obsidian, it won't have cleavage. Instead, it will fracture.
Just break unevenly.
Often, yes. An irregular fracture is common, but some minerals fracture in distinctive ways.
Yeah.
Quartz, for example, and obsidian exhibit conchoidal fracture. They break into smooth, curved surfaces like the inside of a clamshell or broken glass.
Okay, so cleavage is flat breaks, fracture is irregular or curved breaks. What about how it responds to being, say, bent or hammered?
That property is called tenacity. It describes a mineral's resistance to breaking, bending, or otherwise deforming.
So like brittle.
Brittle is one type of tenacity. Minerals like quartz or halite shatter easily, but metals like native copper or gold are malleable, meaning you can hammer them into thin sheets without breaking them.
Ah, related to metallic bonding again.
Exactly. Some minerals like gypsum or talc are sectile, meaning they can be cut into thin shavings with a knife. And minerals like mica are elastic. You can bend thin sheets and they'll snap back to their original shape when you let go.
Malleable, sectile, elastic, brittle. Lots of terms.
They all describe how a mineral holds together under stress.
Okay, one more major physical property. Density. How heavy it feels.
Right. Density is mass per unit volume, how much stuff is packed into a given space. Geologists often use a related measure called specific gravity.
What's that?
Specific gravity is a unitless number representing the ratio of a mineral's weight to the weight of an equal volume of water. So water has a specific gravity of 1. Most common rock-forming minerals, like quartz and feldspar, have specific gravities between about 2.5 and 3.
So 2.5 to 3 times heavier than water.
Correct, but some minerals are much denser. Galena, which is lead sulfide, has a specific gravity around 7.5. Metallic minerals like gold can be incredibly dense. Gold is around 19.3.
Wow, almost 20 times heavier than water.
Yeah. So even a small piece feels surprisingly heavy. You can often get a good sense of relative density just by hefting mineral samples of similar size in your hands. It's another useful clue.
It really is like detective work, using all these clues. Our source also mentions a few other interesting properties that can help sometimes.
Oh, definitely. Some minerals have very distinctive properties. Halite tastes salty, though maybe don't go around licking random rocks.
Good.
Talc feels soapy or greasy. Graphite feels greasy, too. Sulfur often has a characteristic smell, like rotten eggs, especially if you scratch it. Magletite is naturally magnetic. It'll attract a magnet. And a variety called lodestone is a natural magnet.
And calcite has that cool optical trick.
Right. Clear calcite crystals exhibit double refraction. If you place one over text, you'll see two images. And of course, the carbonate minerals like calcite and dolomite will react with the dilute hydrochloric acid they'll fizz, releasing carbon dioxide bubbles.
Each one a subtle clue in this complex identification puzzle. Okay, so we've gone from atoms and bonds to how minerals form and how we identify them in the field. Now let's try to connect all these ideas by looking more closely at mineral structure and how we classify them.
Sounds good.
We've established that a crystal implies that orderly, repeating internal structure. Steno's law, mentioned in the text, notes that the angles between equivalent crystal faces are always the same for a given mineral, reflecting that internal order.
That consistency is key. And this internal structure allows for some flexibility, too. We mentioned compositional variations earlier, how ions of similar size and charge can sometimes substitute for each other.
Like magnesium and iron swapping places in olivine.
Exactly. Olivine has a range of compositions between pure magnesium silicate and pure iron silicate, but the basic structure stays the same. This substitution explains why many minerals aren't just one fixed formula, but can have a range.
So composition can vary slightly,
Mm-hmm.
but can the structure itself vary, even with the same composition?
Yes, absolutely. This is a fascinating phenomenon called polymorphism. Minerals that have the exact same chemical composition but different internal crystalline structures are called polymorphs.
Okay, same ingredients, different arrangement.
Precisely. The classic example is pure carbon. Under relatively low pressure, carbon atoms arrange themselves into sheets with strong bonds within the sheets but weak bonds between them that gives us soft, flaky graphite, the stuff in pencils.
Right.
But under extremely high pressures, deep within the Earth, those same carbon atoms are forced into a much more compact three-dimensional structure where every atom is strongly bonded to its neighbors. And that gives us diamond, the hardest natural substance known.
Wow. Same element, totally different minerals, just based on pressure and structure.
It's incredible. The conditions of formation dictate the structure. This kind of transformation between polymorphs due to changes in temperature or pressure is called a phase change. It shows just how profoundly formation conditions influence a mineral's properties, all stemming from that atomic arrangement.
It really underscores the importance of structure. So this structural and compositional understanding helps us classify minerals, right?
Definitely. We classify minerals into species like quartz, calcite, or olivine. A species is defined by its unique chemical composition and internal structure.
And within a species, you can have varieties.
Yes, varieties are often based on color or sometimes habit. So amethyst and citrine are varieties of the species quartz, distinguished by trace impurities causing their colors.
Okay, species and varieties, and then there are broader groups.
Right. Mineral species are grouped into larger classes based on their principal anion or anionic group, the negatively charged part of their formula. This reflects fundamental similarities in their chemistry and structure.
Like silicates, carbonates.
Exactly. The major classes include silicates containing the SO4 group, carbonates, CO3, oxides, O, sulfides, S, sulfates, SO4, halides like ClF, native elements, pure elements like gold or carbon, and a few others. Minerals within a class tend to share certain structural themes and often occur in similar geological environments.
And when we talk about these classes, it all comes back to the elements that make them up, doesn't it?
It absolutely does. If you look at the abundance of chemical elements in Earth's continental crust, it's dominated by just 8 elements.
Let's see if I remember. Oxygen is number 1.
By a long shot. Oxygen accounts for almost half the weight of the crust. Then comes silicon, number 2.
Oxygen and silicon. O and Psi.
Together, they make up nearly 75% of the crust by weight. After them, in decreasing order, come aluminum, iron, calcium, sodium, potassium, and magnesium. Those 8 make up about 98% of the whole crust.
So everything else is just trace amounts, relatively speaking.
Pretty much. And because oxygen and silicon are so overwhelmingly abundant...
The most common mineral group must be the silicates.
Exactly. Silicate minerals make up well over 90% of Earth's crust. They are the absolute rock stars, the main characters in the story of Earth's rocks.
So what is it about silicon and oxygen that makes them form such dominant and diverse minerals?
It all boils down to their fundamental building block, the silicon-oxygen tetrahedron.
Okay, break that down. Tetrahedron, 4 faces.
Right. Imagine one small silicon ion which has a +4 charge. It's strongly attracted to 4 larger oxygen ions, each with a -2 charge. These arrange themselves around the central silicon ion, forming a compact 4-sided pyramid shape, the tetrahedron. The overall structure has a net negative charge, -4, so it needs to bond with positive ions or other tetrahedra to become stable.
So this little pyramid is the basic unit for all silicates.
It is. And what's truly incredible is how these tetrahedra can then link up with each other. This process is called polymerization.
Polymerization. Like making chains.
Exactly like making chains or sheets or complex frameworks. The tetrahedra link by sharing 1, 2, 3, or even all 4 of their corner oxygen atoms with neighboring tetrahedra.
And these different linking patterns create the different silicate groups.
Precisely. The way the tetrahedra link dictates the mineral structure and drastically influences its properties, like cleavage and hardness.
Can you give examples of these structures?
Sure. At the simplest level, you have independent tetrahedra. They're not linked to each other directly, but are bonded together by positive ions like iron and magnesium holding them in place. Minerals like olivine and garnet have this structure. They tend to be dense, hard, and lack cleavage because the bonds are strong in all directions.
Okay, isolated pyramids. What's next?
Then tetrahedra can link to form single chains by sharing 2 oxygen atoms each. The pyroxene group, like augite, has this structure. Or they can form double chains, sharing alternatingly 2 and 3 oxygens. That's the structure of the amphibole group, like hornblende. These chain structures often lead to cleavage parallel to the chains.
Chains. Makes sense. What else?
Tetrahedra can share 3 oxygen atoms to form continuous sheet structures. This is the basis for the mica group, muscovite, biotite, and clay minerals. The bonds within the sheets are very strong, but the bonds between the sheets are very weak.
Ah, that's why mica peels into sheets and why clays feel slippery.
Exactly. Talc, another sheet silicate, feels incredibly slippery because of those weak bonds between the sheets. Finally, if all four oxygen atoms in each tetrahedron are shared with neighbors, you get complex three-dimensional frameworks.
Showing everything.
Right. This creates strong, stable structures like those found in quartz, which is pure SiO2 framework, and the feldspar group, the most abundant group in the crust. These framework silicates tend to be quite hard and resistant.
So isolated chains, sheets, frameworks. That explains the huge diversity. Now, within the silicates, geologists often make a big distinction based on color and chemistry, right? The light versus the dark silicates.
That's a very important practical distinction. We divide them into the light silicates, also called non-ferromagnesian, and the dark silicates, ferromagnesian.
Ferromagnesian, meaning iron and magnesium.
Exactly. The dark silicates contain iron, Fe, and/or magnesium, Mg, in their structure. This gives them their characteristic dark colors, typically black, brown, or green, and a higher specific gravity because iron and magnesium are relatively heavy elements.
Okay, dark and dense, and the light silicates.
The light silicates generally lack significant iron and magnesium. Instead, they contain more abundant lighter elements like aluminum, AO, potassium K, calcium Ca, and sodium A. As the name suggests, they are typically light in color, white, pink, gray, or colorless, and have a lower specific gravity.
Let's run through some key examples of each, starting with the light silicates.
Okay, top of the list has to be the feldspar group. This isn't just one mineral, but a group, the most abundant mineral group in Earth's crust, making up over half of it.
Wow, feldspar.
They're framework silicates, generally hard, around 6 on Mohs scale, with two directions of cleavage meeting at about 90 degrees. There are two main types: potassium feldspar, often pink or white, and plagioclase feldspar, ranging from white to gray, sodium and calcium rich.
How can you tell them apart?
A key trick is to look for striations, fine, parallel lines like tiny grooves on some cleavage surfaces of plagioclase. Potassium feldspar doesn't have these.
Striations on plagioclase. Got it.
uh.
What's another major light silicate?
Quartz. We've mentioned it a few times. Pure silicon and oxygen, SiO2, another framework silicate. It's known for being hard, 7 on Mohs, very durable, lacking cleavage, it fractures conchoidally, and having that glassy luster. Its many colors, as we said, are due to tiny impurities.
So, feldspar and quartz dominate. What else?
Muscovite. This is the common light-colored mica. It's a sheet silicate, easily recognized by its pearly luster and its perfect cleavage in one direction, letting it split into thin, flexible, often transparent sheets.
Okay. Any others?
Clay minerals are also light silicates. They're a whole group of sheet silicates, typically formed by the weathering of other silicate minerals, so they're major components of soil. They're usually very fine-grained, feel earthy, and some types, like those used in kitty litter, swell up when they absorb water. Kaolinite is a common clay used in making china and coating paper. It's even used sometimes to thicken milkshakes.
No way. Okay, feldspar, quartz, muscovite, clays, those are the main light ones. Now for the dark ferromagnesian silicates.
Right. First up is olivine. It has that isolated tetrahedral structure, typically black to olive green in color, glassy luster, conchoidal fracture, no cleavage, often occurs as small granular crystals. It's common in dark igneous rocks like basalt and makes up much of Earth's upper mantle. The gemstone variety is peridot.
Olive green. Olivine. Makes sense.
Then the pyroxene group, with augite being the most common member. Single chain structure, usually black or very dark green, opaque, with two cleavages that meet at nearly 90 degrees. Tends to form blocky-looking crystals.
Augite. Blocky, 90-degree cleavage. Next.
The amphibole group and hornblende is the common one here. Double chain structure. Also typically dark green to black, but its two cleavage directions meet at angles of about 120 degrees, which is a key difference from pyroxene. Also, hornblende crystals are often more elongated or needle-like compared to augite's blocky shape.
Okay. Hornblende 6012 cleavage, elongated. Got it.
Then we have biotite, which is the dark-colored mica. Like muscovite, it's a sheet silicate with perfect cleavage in one direction, splitting into thin sheets, but it's black or dark brown due to iron and magnesium in its structure. Still has that shiny luster on the cleavage surfaces.
Dark mica. Easy enough. One more.
Let's add garnet. Like olivine, it has that isolated tetrahedral structure. It's known for its glassy luster, lack of cleavage, it fractures, and often forms beautiful equidimensional crystals, commonly 12-sided. While deep red is the classic garnet color, it actually comes in almost every color depending on its specific composition.
So olivine, pyroxene, amphibole, biotite, garnet, the main dark silicate players, each telling a story about the rock it's in and the conditions it formed under. So it's clear silicates are the vast majority, the main event in Earth's crust. But we can't completely ignore the non-silicate minerals, can we?
Absolutely not. Even though they make up less than 10% of the crust, they are incredibly important, especially economically. Many of our most vital resources come from non-silicates.
Okay, let's quickly touch on the main non-silicate groups. You mentioned carbonates earlier.
Yes, the carbonate minerals all contain the carbonate ion, CO3 too. The most common are calcite, calcium carbonate, CaSO3, and dolomite, calcium magnesium carbonate. These are the main constituents of the sedimentary rocks limestone and dolostone, respectively. They're crucial for making cement and lime, and as we noted, they famously fizz when dilute acid is applied.
Fizz test for carbonates. What other groups?
We have sulfates, containing the sulfate ion, SO4 Gypsum, hydrated calcium sulfate, is a very common one, used to make plaster and wallboard. Halides contain halogen elements like chlorine, Cl, or fluorine, F. Halite, sodium chloride, NaCl, table salt is the prime example, often forming from evaporating seawater. Sylvite, potassium chloride, is another halide, important for fertilizer.
Salt and fertilizer, definitely important.
Then oxides, which contain oxygen bonded to one or more metals. This group includes crucial metal ores like hematite and magnetite, iron oxides, and corundum, aluminum oxide, the mineral form of ruby and sapphire.
Iron ores, ruby, sapphires.
Wow. Sulfides contain sulfur, S, bonded to a metal. Many important metal ores are sulfides, like galena, lead sulfide, sphalerite, zinc sulfide, and chalcopyrite, copper iron sulfide. These often have metallic lusters.
Lead, zinc, copper, more vital metals.
And finally, the native elements group, which are minerals composed of just a single element, found in pure or nearly pure form. We've mentioned gold, copper, and diamond carbon. Sulfur and graphite carbon, again, also occur as native elements.
So even though they're a smaller percentage of the crust overall, these non-silicates are where we get a huge amount of our industrial metals, building materials, chemicals, and gemstones.
Exactly. The economic importance is immense. The source material even has a feature on gemstones, distinguishing between precious ones like diamonds, rubies, sapphires, emeralds, which are rarer and harder, and semi-precious stones. It highlights how ruby and sapphire are just colored varieties of the oxide mineral corundum, and how diamond, besides being a gem, is a vital industrial abrasive because of its extreme hardness, which comes right back to its unique crystal structure and bonding. It really shows the dual nature of many minerals, geologically interesting and economically vital.
What an incredible journey. We've really gone from the tiniest atomic particles and the bonds between them all the way up to these vast mineral groups that form the bedrock of our planet.
It's quite a scope.
Yeah, we've seen that minerals are these naturally occurring, generally inorganic solids. They have that crucial, orderly, crystalline structure and a definite chemical composition, more or less.
Built from atoms held together by ionic, covalent, or metallic bonds.
Right. And they form through diverse processes like precipitation from water, crystallization from molten rock, or even through biological activity.
And we identify them using this whole suite of physical properties: luster, streak, hardness, cleavage, fracture, density, and others, all reflecting that internal structure and composition.
It really drives home that every single mineral, with its unique set of characteristics derived from its atomic structure, is a truly foundational piece of our world. It affects everything from, the stability of continents and the occurrence of earthquakes to the function of the technologies we rely on every single day.
Absolutely. And perhaps this raises an important question for you, the listener, to think about.
Yeah.
Consider just how deeply intertwined Earth's geological processes, mountain building, erosion, volcanism are with the behavior of these tiny fundamental building blocks we call minerals. Every time you see a mountain range, feel the ground beneath your feet during a tremor, or even just look at the components inside your phone or computer. You're experiencing the direct, large-scale outcome of matter and minerals behaving exactly as their atomic structure dictates. So maybe ask yourself, what other everyday objects do you use that rely critically on the unique properties of a specific mineral? And what is it about that mineral, its hardness, its conductivity, its chemical reactivity, that makes it the right material for that particular job?
That's a great thought to leave us with, connecting the geology to our daily lives in unexpected ways.
It's all connected.
Well, thank you for joining us in this deep dive into the fascinating world of matter and minerals. We really hope you feel a little more well-informed and maybe a lot more curious about the very ground beneath your feet.